I was looking back at the calendar for October 2011 recently, and it really struck me. It was this bizarre pivotal moment in tech history.
Oh, absolutely.
It was one of those weeks where the world really shifted, but half of the shift was screamingly loud and the other half was almost completely silent.
It was a perfect study in contrast, isn't it?
Yeah.
You're talking about the week that digital age lost two of its founding fathers, really.
Exactly. But the way we handled it, the way the world reacted was just so different. On one side, you had Steve Jobs. When he died on October 5th, it was a global event.
A phenomenon.
A total phenomenon. I remember walking past the Apple store downtown, and the windows were just, plastered with sticky notes. People were crying in the streets. It was front page news in every single language. It felt like a head of state had died.
It really did. And in a way, it made sense. Jobs was the face of the technology we touch, the technology we hold. He was the showman.
The ultimate showman.
He'd hold the device up in his hand and tell us it was magic. And we believed him. We felt this personal connection to the guy in the black turtleneck because he was the one selling us the future.
Then, just 7 days later, literally a week, around October 12th, another man died. He was 70 years old, living alone in a town called Berkeley Heights, New Jersey. His name was Dennis Ritchie.
Crickets.
Almost total silence. Unless you were a serious computer nerd, a programmer, you probably didn't even see the headline. It was buried. If it was there at all.
And that silence, I think, is actually quite profound. It speaks volumes about the nature of his work. While Steve Jobs was designing let's call them the fashion items of the tech world, the beautiful, sleek glass rectangles,
right?
Dennis Ritchie was doing something much, much deeper. He wasn't designing the case. He was designing the physics of the entire digital universe that lives inside that case.
That's the core of what we want to get into today. This claim that this quiet guy who nobody stopped to mourn in the street actually built the, quote, numeric soul of the device in your pocket right now.
It's not just a claim, It's the reality of the situation. If you could take a powerful enough microscope and look inside the logic of your iPhone or your smart fridge or the massive servers running this very conversation,
you wouldn't see Steve Jobs.
You would not. You would see the work of Dennis Ritchie everywhere. His fingerprints are on every single chip.
So if he's that fundamental, why is he the unsung hero? Why don't we have movies about him written by Aaron Sorkin? Why isn't he a household name?
Because infrastructure is invisible when it works perfectly. You only notice the plumbing when a pipe bursts. Right. You only think about the power grid when the lights go out. Dennis Ritchie built the plumbing for the entire information age.
So for this deep dive, we're going to unpack that. We're going to figure out how one man, working in a probably messy office at Bell Labs, created the two most important, most foundational tools in computing history: the Unix operating system and the C programming language.
The twin pillars.
Yeah, and I hear those names Unix and C, I vaguely know they're important. But I want to get past the Wikipedia summary today. I really want to understand why they matter. Because I've heard people, serious people, say that without Ritchie, the internet as we know it simply wouldn't exist.
And that's not hyperbole. It's a statement of fact. Brian Kernighan, who worked right alongside him, famously said that the tools Ritchie built and their direct descendants run pretty much everything today.
Everything.
Everything. So our mission here is to find out how that happened.
Yeah.
And it really has to start with understanding who Dennis Ritchie actually was as a person.
Right, because he wasn't a Silicon Valley dropout, was he? He didn't start some company in a garage with the goal of getting rich.
Oh, not at all. He was from a completely different world, a different mindset.
Yep.
Dennis McAllister Ritchie was born in 1941 in Bronxville, New York. And he was basically born into the family business of science and engineering.
His father was also in the field.
His father, Alistair Ritchie, was a legend in his own right, a longtime scientist at Bell Labs.
The same Bell Labs.
The very same. Alistair co-authored a really important book called The Design of Switching Circuits. Now, that sounds incredibly dry, I know.
Does this sound a little dry, yeah?
But switching circuits are the fundamental logic of how machines make decisions. It's the physical manifestation of 0 and 1, on and off, true and false. Dennis literally grew up in Summit, New Jersey, with that kind of deep structural thinking just floating around the dinner table.
So he was steeped in this idea of logical structures from the time he was a kid. It wasn't something he discovered in college.
Completely. It was his native language. And of course, he was a brilliant student. He went to Harvard, graduated in 1963. But here's the key distinction, and this is so important for understanding his later work. He didn't study computer science.
Because the major didn't exist yet.
It barely existed as a concept. He studied physics and applied mathematics. And I think this is absolutely crucial for understanding how his mind worked.
How so?
Well, computer science today can sometimes feel more like engineering. You're gluing different libraries and frameworks together to build a product. But physics and pure math, they're about discovering fundamental truths. They're about finding the cleanest, the most elegant, the simplest possible equation to describe a complex universe.
And you're saying you can see that elegance in his code later on?
You absolutely can.
Yeah.
There's a minimalism and a power to his work that is just beautiful. It's not messy. It's incredibly disciplined. He approached software not as a hacker trying to make something work for a demo, but as a mathematician trying to find the correct and most fundamental solution to a problem.
Okay, so speaking of his time at Harvard, there's this really weird story about his PhD that I was reading about. The notes say he sort of lost his degree. How on earth do you lose a PhD?
This is one of those anecdotes that perfectly encapsulates his personality. So in 1968, he's at Harvard. He writes his entire thesis. It's got this very academic title, Computational Complexity and Program Structure.
Sounds impressive.
It was supervised by a big name, Patrick Fisher. He does all the research. He writes the draft. He submits it. He's done all the hard work. But he never officially received the degree at the time.
So what happened? Did he fail his defense or something?
No, nothing like that.
Oh,
He just didn't bother with the final administrative wrap-up. The story goes that he didn't want to pay the binding fee to have a fancy copy put in the library, or he just didn't file the final piece of paperwork. He already started working at Bell Labs, and he was so completely engrossed in the actual real-world problems there that the piece of paper, the credential itself, it just didn't matter to him.
That is the ultimate nerd flex. I'm literally too busy inventing the future to go pick up my diploma from the registrar's office.
It is. And for decades, people thought the thesis was actually lost. It became this kind of biographical mystery, a holy grail. Then, just a few years ago, in 2020, the Computer History Museum worked with his family and finally dug it up from his home. But it just shows you where his head was at. He wasn't chasing titles or accolades. He was chasing interesting problems.
And he went to chase those problems at Bell Labs.
I feel like we need to pause on Bell Labs for a second. We all hear the name. But in the 1960s, what was this place really? Was it just a corporate lab?
It was Mecca. It was the absolute engine room of American and really global innovation for half a century. You have to imagine a place that had the nearly unlimited funding of a massive corporation, AT&T, but the intellectual freedom of a top-tier university.
That's a rare combination.
Incredibly real. You could walk down the hallway and bump into a guy who had just won the Nobel Prize for discovering the cosmic microwave background radiation, and then go have lunch with the team that was inventing the laser. The transistor was invented there. Information theory was born there.
It sounds like a playground for geniuses.
It was. And the management style was completely unique. They basically hired the most brilliant people they could find and said, go do something interesting, we trust you. They didn't have these quarterly product targets or marketing-driven deadlines in the same way companies do today. And that freedom is the only reason Ritchie and his colleagues were able to do what they did. So he lands at Bell Labs, and he meets Ken Thompson. And this is the partnership that changes everything.
Lennon and McCartney of computing.
Right. And they start working on this project called Multics. What was that?
Okay, so Multics, the name stands for Multiplexed Information and Computing Service. This was the Apollo program of computing in the 60s, a moonshot. It was this massive joint project between Bell Labs, MIT, and General Electric.
What was the goal?
They wanted to build a computing utility. The idea was that computing would be like electricity or water. You just plug your terminal into the wall, and this massive mainframe somewhere else would serve up computing power to hundreds of users at once.
That sounds suspiciously like the cloud or time sharing.
It was a proto-cloud. It was an incredibly visionary idea. But the problem was they tried to do everything at once. The system became monstrously, unbelievably complex. It was slow. It cost a fortune to run. It was a classic case of design by committee on a grand scale.
And Bell Labs, despite having deep pockets, eventually got sick of burning money on it.
They pulled the plug. In 1969, they officially withdrew from the Multics project. They just realized it was a bottomless pit. So suddenly, Ritchie and Ken Thompson, who'd been living in this world for years, were left with nothing. No project, no massive mainframe to play with.
This seems like the moment where most people in a big company would just, dust themselves off and go find another corporate assignment. Okay, boss, tell me what to work on next.
But they didn't. They were frustrated. They had tasted what an operating system could be, something interactive, something that let multiple people work at once, and they did not want to go back to the old way of doing things.
And what was that old way? Remind us what they were trying to avoid.
The alternative was called batch processing, and it was soul-crushing. Imagine you want to run a program. You can't just type it. You have to punch your code onto a stack of physical cards.
Like with holes in them?
Exactly. A stack of punch cards. You take your stack of cards to an operator, a guy in a white lab coat behind a big glass wall. You hand them over. He puts them in a queue with everyone else's jobs. You come back 6 or 8 hours later, and he hands you a printout that says, "Error on line 3."
That sounds like actual hell. The feedback loop is hours long.
It was an incredible amount of friction. Multics, for all its flaws, was supposed to be interactive. You type a command, the computer responds instantly. So when Multics was canceled, Thompson and Ritchie were desperate to keep that interactive environment alive. And Ken Thompson found an old, discarded computer in a corner of the lab, a PDP-7.
A discarded computer, not the latest and greatest.
Far from it. It was already obsolete, sitting unused. It was a mini computer, which in 1969 meant it was only the size of a few filing cabinets, not an entire room. But it had terrible memory, very little processing power. The key thing, though, was that it was theirs. Nobody was watching them. No management oversight.
So they start building their own operating system. Was it just for fun? Was there a business case?
Not at all. It was for utility, born of necessity. Thompson had written this game he liked called Space Travel, which simulated the physics of flying through the solar system.
Our video game.
Basically, yeah. And running it on the other available systems was expensive and clunky, so he decided to port the game to the little PDP-7. But to do that effectively, the machine needed a basic operating system, a file system. So Thompson starts writing one, and Ritchie joins in. They started stripping away all the insane complexity of Multics and keeping only the clean, simple ideas.
And this is where the name comes from, right? This is a great story.
It is. Their colleague, Brian Kernighan, who we mentioned earlier, joked that since the bloated Multics was multiplexed, meaning many things at once, this new, scrappy, minimalist system was the opposite. It was uniplex. It did one thing.
Single tasking system.
Right. So he called it Unix, U-N-I-C-S, as a pun. And that eventually got stylized as UNIX.
The most important piece of software in the world started as a dad joke.
A nerd pun, yes. But the name perfectly reflected the philosophy. And this is where we really need to dig in, because the Unix philosophy is the idea that truly changed the world. Multics tried to be a Swiss Army knife with 1,000 blades that was so heavy you couldn't lift it. Unix was a kitchen drawer full of individual, really sharp knives.
Okay, break that analogy down for me. What does that mean in practice?
The Unix philosophy in a nutshell is this. First, write programs that do one thing and do it well. Second, write programs that can work together. Third, write programs to handle text streams, because that is a universal interface.
Can you give me a real-world example of what that looks like?
Absolutely. Let's say you have a huge text file, maybe a whole book, and you want to find every unique word in that book that contains the letter Z, sort them alphabetically, and then count how many there are.
Okay, a pretty specific task.
In the old way of thinking, you'd have to write a single, massive, complex program from scratch to do specifically that one task. In the Unix way, you use small tools and connect them with a concept called a pipe. You take a small program that just reads text. You pipe its output to another small program that just finds words matching a pattern. You pipe that output to a program that just sorts lines of text. You pipe that to a program that removes duplicates. And finally, you pipe that to a program that just counts lines.
It's like a digital assembly line. Each station does one simple job.
Precisely. You chain these small, simple, single-purpose tools together to accomplish a complex task. This concept of the pipe, represented by a vertical bar on the command line, was utterly revolutionary. It meant you didn't have to reinvent the wheel every time you had a new problem. You just rearranged the Lego blocks you already had.
And Ritchie's role in this was what?
He was crucial. While Thompson wrote a lot of the initial kernel and commands, Ritchie was deeply involved in the design philosophy, and very importantly, he was the primary designer of the Unix file system.
What was special about the file system?
The big idea was everything is a file. Your document is a file, obviously, but in Unix, your keyboard is also treated like a file. The screen you're typing on is a file. The printer is a file. Even the processes running on the system are represented as files. This incredible abstraction made the system unbelievably simple and flexible. You could use the same tools to read from a document as you did to read from the keyboard.
Okay, so they have this cool, elegant OS running on their junker PDP-7 in a closet in New Jersey. But that's a long way from running the entire world. How does it escape the lab?
That is the next great revolution, porting. See, back then, if you wrote software for a specific computer, like a PDP-7, it only ran on a PDP-7. It was completely locked to the hardware. The code was written in what's called assembly language, which is tied directly to the wiring and instruction set of that specific machine.
So if Bell Labs bought a new, better computer a year later, all their Unix work would be trash.
Basically, you'd have to start over and rewrite the whole thing from scratch for the new machine's architecture. It was a huge problem. Ritchie and Thompson did something that was considered heretical at the time. They decided they wanted to move Unix to a newer, more powerful machine, the PDP-11. But to do that effectively, they knew they needed a way to write the operating system in a language that wasn't tied to any one piece of hardware.
And this is the bridge to the next huge topic. They needed a new language.
Yes, this is the moment. To make Unix universal, to make it so it could live on any computer, past, present, or future, Dennis Ritchie had to invent the C programming language.
All right, this is the part I've been dreading a little bit because I'm not a coder. I hear C and my brain just sees semicolons and error messages. How do we explain the importance of C to someone who has never written a line of code?
Let's stick with analogies.
Yeah.
We talked about assembly language before. Imagine you want to build a simple brick wall. Assembly language is like giving instructions to a robot, where you have to specify the movement of every single muscle fiber in its body. Contract bicep by 20%, rotate wrist exactly 4 degrees, grip brick with 10.2 newtons of force, extend arm.
That sounds absolutely exhausting. And if you get one muscle twitch wrong, you drop the brick and the whole thing fails.
Precisely. And even worse, if you get a new, different model of robot, none of those muscle instructions make any sense anymore because the new robot has different arms and motors. That's assembly. It's incredibly fast and powerful if you get it right, but it's tedious, error-prone, and completely tied to one specific machine.
So what's the opposite of that? What's a high-level language?
A high-level language like Python or JavaScript today is like telling a human contractor, build me a 4-foot-high brick wall right there. The contractor handles all the details of muscles and mortar. It's easy for you, the boss, to give the instruction, but you lose fine-grained control. Maybe the contractor builds it a bit slower than you'd like or uses a bit too much mortar. It's abstract and easy, but less efficient.
Okay, so we have the micromanaging robot and the independent contractor. Where does C fit in this picture?
C is the perfect middle ground. It's like you, the human, are wearing a powered exoskeleton. You are still moving the bricks yourself. You have all that direct control and speed and power, but the suit handles the tedious micromuscle movements for you. It lets you think in terms of pick up brick and place brick, and it translates those concepts into the machine's native instructions with incredible efficiency.
So it's powerful and fast like the robot, but readable and logical like a human instruction.
That's the magic of it. Ritchie created a language that was close to the metal, as programmers say. It allowed you to do things that were previously only possible in assembly, like managing memory addresses directly, which is risky but very powerful, while still using logical words and structures that humans can understand, like if, then, while, and for.
You mentioned memory addresses. Why is that so important? I mean, today, I just save a file. I don't have to think about where on the hard drive it goes.
In the 1970s, you absolutely had to think about it. Memory was scarce and incredibly expensive. A core innovation in C was the concept of pointers. A pointer is basically just a variable that holds a memory address. It allowed a programmer to say, hey, don't copy this entire massive encyclopedia from one part of memory to another new spot. Instead, just create a little note that points to the encyclopedia that's already on the shelf over there.
So it saved a ton of space and time.
A massive amount. It made programs incredibly fast and efficient. But it also made them dangerous.
How so?
Because if you're not careful, your pointer could point to the wrong shelf. Or you could change the data on the shelf when another part of the program was still expecting the old data to be there. Or you could forget to clean up the shelf when you're done, leading to memory leaks. This is the great trade-off of C53. Ritchie gave programmers a chainsaw. Yes. It's an unbelievably powerful and efficient tool. You can build a log cabin in record time. But if you're careless for a split second, you can cut your own leg off. Many modern languages have safety guards on the chainsaw. C does not. It assumes you're an expert and trusts you with the full power of the machine.
And this language, C, was what allowed them to finally move Unix off that one machine.
This was the absolute game changer. They rewrote almost the entire Unix kernel and all its utilities in C. This was unheard of. Operating systems were supposed to be written in assembly. But by rewriting it in C, The operating system was suddenly no longer a PDK-11 thing. It was a software thing. It was abstract.
So if you wanted to run Unix on a brand new supercomputer from a different company.
You just had to do one relatively small job.
Hmm.
Write a C compiler for that new machine. A C compiler is a program that translates C code into that specific machine's native language. Once you had that compiler, the entire Unix operating system, millions of lines of code, would just compile and run.
This broke the monopoly that hardware manufacturers had on software.
It completely destroyed it. It decoupled the software from the hardware. It meant that software was now portable, independent of the machine it ran on. In a sense, it commoditized the hardware. The value shifted from the box to the code running inside it.
This brings us to the book. When I was preparing for this, I was told I absolutely have to ask about K&R.
Ah, yes. The White Book. The C programming language, published in 1978, written by Brian Kernighan and Dennis Ritchie. In the industry, to this day, it is known simply as K&R.
What is it, just a textbook, a manual?
It's so much more than that. It is a masterpiece of technical writing. Most computer manuals then and now are like reading a tax code. They are thick, dense, and impossible to get through. K&R was thin. It was concise. It was beautifully, clearly written. It didn't just teach you the syntax of the language. It taught you the style and the philosophy.
It set the vibe for the entire C programming community.
It absolutely did. It preached clarity over cleverness. Simplicity. Don't write tricky code. Write clear code. That book is still on the shelves of professional software engineers today, almost 50 years later. Yeah. It's a classic for a reason.
So now we have the two pillars in place. We have the OS, Unix, and the language C. Now let's fast forward. We need to connect the dots. Why does the person listening to this on an iPhone 16 or an Android phone owe Dennis Ritchie a thank you?
Okay, let's trace the family tree. And it's actually shocking how direct the lineage is. Let's start with Unix. Ritchie himself said in an interview late in his life that he views Linux as a direct and healthy continuation of Unix ideas.
And Linux today is everywhere.
Linux runs the internet. The vast majority of servers that make up the cloud, Amazon, AWS, Google Cloud, Microsoft Azure, they all run on Linux. So every time you stream a movie on Netflix, do a Google search, use an AI chatbot, you're using a system that is, for all intents and purposes, a clone of Unix.
What about the phone in my pocket? Let's start with Android.
Android uses the Linux kernel.
Hold on, define kernel for us. I hear that word all the time, but what is it really?
The kernel is the core. It's the absolute heart of the operating system. It's the first piece of software that loads when the computer boots up, and it's the piece that talks directly to the hardware. It manages the CPU, the memory, the battery, the radios, the interface you see, the buttons and icons you click. That's like the body of the car. The kernel is the engine.
So Android's engine is Linux.
Which is a Unix clone. So every Android phone is a Unix machine.
Okay, what about Apple? Apple is famous for being the odd one out. They always like to do their own thing, the think different mantra.
Not here they don't. This is the ultimate irony. Steve Jobs' greatest software achievement, macOS and by extension iOS, which runs the iPhone and iPad, is built directly on top of a system called BSD.
And BSD is?
Berkeley Software Distribution. And what is BSD? It's a version of Unix that was developed at the University of California, Berkeley in the 1970s, based on the original source code from Bell Labs.
So you're telling me when I slide to unlock my iPhone, deep, deep down in the basement of that software,
it's Dennis Ritchie's logic. In fact, if you open the Terminal app on any Mac today, you are dropped into a Unix command line. You can type commands like ls to list files or grep to search for text. The very same tools with the very same names that Ritchie and Thompson designed on a PDP-11 in 1971.
That is just wild. It's like finding out that the engine in a brand new Tesla is actually a steam engine from the 1800s, but, you know, in a good way.
It's more like finding out that the laws of physics that govern the Tesla's electric motor are the same ones Newton discovered 300 years ago. Ritchie didn't just invent a product. He discovered and defined the fundamental physics of how modern software should be structured. And then there's the other side of it, the C family tree.
Right, because C itself isn't really used for writing most iPhone apps anymore, is it? Programmers use newer languages like Swift.
You write the app in Swift, yes. But the Swift compiler, the tool that takes your human-readable Swift code and turns it into an app the iPhone can actually run, is written in C++ Mark. And what is C++? It's literally just C with a bunch of extra features bolted on. It was originally called C with classes.
So C is building the tools that build the apps.
It's the foundation of the whole tool chain. What about Java, the language that runs huge corporate systems and was the original language for Android apps? Its syntax is based directly on C JavaScript, the language that makes the entire web interactive. C-style syntax. Python, the language of data science and AI. The main Python interpreter, the program that actually runs Python code, is written in C.
So it really is the DNA.
It is the absolute genetic ancestor. Every single major programming language in use today is either a direct descendant of C, is heavily influenced by C's syntax, or is built using tools written in C. If you could magically delete the C language from history, the entire software tower of Babel we've built for the last 50 years would just collapse into dust.
I remember reading one commentator who said Ritchie co-invented the DNA of effectively every single computer software product we use. I honestly thought that was an exaggeration when I first read it.
It's not. It's probably an understatement.
Yeah.
Doug McElroy, one of their brilliant colleagues at Bell Labs, put it best. He said, "The names of Ritchie and Thompson may safely be assumed to be attached to almost everything not otherwise attributed."
Meaning, if you look at a piece of foundational software and you don't know who built it, it was probably them.
That's the gist of it.
Yeah.
Their influence is the default.
I want to pivot a bit to the man himself, because usually when you have someone this influential, Steve Jobs, Bill Gates, and Elon Musk, they are these massive, complicated, often difficult personalities. They seek out the spotlight. They want the credit. Dennis Ritchie seems different.
He was the absolute antithesis of the modern tech bro CEO. He was quiet. He was famously humble. He lived alone. He wasn't trying to disrupt industries or make billions of dollars or become a celebrity. He was a scientist. He just wanted to build better tools for himself and his friends.
There's this story about the NSA that I think is just incredible. It feels like it's pulled from a spy thriller for a second.
It really does. So in the 1970s, Ritchie was also dabbling in cryptography, because of course he was. He was working with two colleagues, James Reeds and Robert Morris, on what's called a ciphertext-only attack.
Which means cracking a secret code without having the decryption key, right?
Exactly. You just have the scrambled messages. And they were targeting the U.S. M209 cipher machine. This was a mechanical encryption device used by the U.S. military during World War II and the Korean War. It was supposed to be secure. Well, Ritchie and his team wrote a program that could crack it. They figured out that if they had about 2,500 letters of coded text, they could solve it.
That's a huge deal. They basically proved a piece of U.S. military encryption hardware was fundamentally broken.
It was a massive discovery. So they wrote a formal paper on it. They were getting ready to publish it in an academic journal. And then the NSA, the National Security Agency, came knocking on Bell Labs' door.
The actual men in black.
Pretty much. They came and they had a quiet conversation with Ritchie and Bell Labs management. And they said, look, we know you cracked it. We're not surprised. But you cannot publish this paper.
And their reason was?
Their reason was that several foreign governments, some of them adversaries of the United States, were still using that same M209 machine because they thought it was secure. The NSA was happily reading their mail. If Ritchie published his paper, these governments would find out their codes were broken, they'd switch to a new system, and a valuable source of intelligence would go dark.
Wow. Okay, so this is a real ethical dilemma. This is the moment where the modern information wants to be free. Hacktivists would just dump the paper on the internet anyway. Consequences be damned.
Right. You can imagine that happening today. But what did Dennis Ritchie do? He just said, okay. And he put the paper in a drawer, and it stayed there, unpublished, for decades.
He didn't fight it. He didn't argue for academic freedom.
No. He just complied. He wasn't an anarchist. He was a scientist, but he was also a pragmatist. He didn't have this massive ego that needed the fame of being the guy who beat the NSA. The intellectual challenge was solved. That was enough for him. So he just went back to work on Unix.
That humility seems to be the central theme of his life. He wins the Turing Award in 1983, which is...
the Nobel Prize of Computing. The highest honor.
He gets the National Medal of Technology from President Bill Clinton in 1998. The citation says he stimulated the growth of an entire industry. But he never really cashed in, did he?
Never. He stayed at Bell Labs, which later became Lucent his entire career. He was managing a small research group towards the end, but he was still writing code. He wasn't on the board of directors. He wasn't doing a book tour or giving TED Talks. There's a visual description of him that I love from his colleagues. He was often just seen walking the halls in a simple striped sweater, sometimes with a big beard, looking like a slightly distracted but very calm professor.
The calm genius archetype.
Exactly. And he was incredibly generous with credit. Whenever people interviewed him about Unix or C, he would constantly deflect the praise. He'd insist that Unix was just a continuation of ideas from Multics and other systems. He refused to take sole credit. He always pointed Ken Thompson to Brian Kernighan, to the whole collaborative environment of Bell Labs.
Which makes the end of his life and the lack of public recognition even more poignant. We talked about the timing, October 2011.
Yeah, it was a rough end. He had been in frail health for a while. He was battling prostate cancer and heart disease. He died alone in his home. The news actually broke because Rob Pike, another former colleague and a giant in the field himself, posted about it on Google plus Skip.
Google plus Gate, wow, that dates it right there.
It really does.
Yeah.
And because the entire global media machine was in the middle of this week-long deification of Steve Jobs, the obituaries for Ritchie were small. They were footnotes.
But the tech community, the people who actually build things, they knew.
Oh, they knew. The tributes from that community were quiet, but so heartfelt. And they were geeky and beautiful. The Fedora 16 Linux distribution, which was released a month after he died, was officially dedicated to his memory. FreeBSD 9.0, another major open-source operating system, was also dedicated to him.
And my personal favorite tribute.
The asteroid, yes. In 2012, astronomers Tom Glanos and David H. Levy officially named asteroid 294727 Dennis Ritchie.
So he's literally floating out there in the cosmos.
His legacy is in the sky and in the cloud that runs on his OS and in the phone in your pocket. He's everywhere.
I want to circle all the way back to that comparison we started with, Jobs versus Ritchie. Now that we've gone through this whole history, how do you see it? It feels like we need both types of people, but our culture over-indexes so heavily on one of them.
That is the perfect way to put it. We over-index on the visionary marketer. And Steve Jobs was a genius at that. Let's not take anything away from him. He understood human psychology. He understood desire. He knew how to package technology into a beautiful, simple object that we would fall in love with. He was a master of the user experience. But Ritchie was the visionary architect. He understood the structural integrity of the entire digital world.
The Economist had that great line in his obituary. The gizmos of the digital age owe a part of their numeric souls to Dennis Ritchie.
And the Deccan Herald, a newspaper in India, went even further. They just flat out said Ritchie was far more influential than Jobs. And you can make a strong case for that.
What's the case?
Here's the litmus test I always use. If Steve Jobs had never existed, your smartphone today would almost certainly look different. Maybe you'd have a physical keyboard. Maybe the interface wouldn't be as slick. But it would very likely still exist in some form. Another company would have figured it out. But if Dennis Ritchie had never existed,
We might still be punching cards.
it's a real possibility. Or, more likely, we would be stuck in a horribly fragmented world of proprietary, incompatible systems where nothing talks to anything else. The internet as we know it, which relies on open standards and portable software that can run on any machine, might have been impossible.
Ritchie gave us the universal language and the universal blueprint.
It really makes me think about where we are today in the tech world. Ritchie and his colleagues worked in this open, collaborative environment. Bell Labs shared the Unix source code with universities for free, basically. They wanted people to play with it, to learn from it, to improve it.
It was an academic project, not a commercial one.
Exactly. And now you look at our phones. They are the definition of walled gardens. They have locked bootloaders. They have app stores that you cannot bypass. The hardware is sealed shut. That is the big, final, provocative question for you, the listener, to think about. We built this entire modern world on the back of Ritchie's open, modular, tool-based philosophy. But the dominant companies of today are increasingly locking that world down into closed, proprietary ecosystems. Are we still funding the kind of fundamental, curiosity-driven research that allows a Dennis Ritchie to play with a junker PDP-7 for a year with no immediate commercial goal?
Or are we just funding the next iteration of the shiny fashion item?
Exactly. Are we building foundational tools for the future, or are we just building disposable products for today? Ritchie built tools, and tools are what empower the next generation to build something that we can't even imagine yet.
That's a heavy, important thought to end on. I can guarantee that the next time I pick up my phone, I'm not going to see the screen and the apps. I'm going to be thinking about the engine underneath it all.
Think about the Unix philosophy. Think about the C code running the kernel. Think about the quiet guy in the striped sweater. Think about Dennis.
Thanks so much for taking us through this deep dive.
It's always a pleasure. His is a story that needs to be told.